So I'm Saim Abbas. I'm a PhD student. I'm from IIT Bombay and I'm working with Professor Nagamani Jaya Balila and under Sudhanshu Mallick and Professor Sanjay Sampath from Stony Brook. He gave us the coatings for the purpose of these experiments and for my thesis. And I would like to acknowledge the Pratt& Whitney for funding and the central facilities of IIT Bombay and PWRDC Bangalore for microstructural characterizations. So I'll start with the failures of the coatings that happen in the thermal barrier coatings. I'll talk about only cohesive and adhesive failures in my cases. And there are other mechanisms that can happen in the coatings that with which it can fail. But when there is a thermal or mechanical stresses, when there will be developed inside the coatings, there is a possibility of getting a vertical crack or an interface crack, apart from other failures. So in these cases, whenever there is a loading, there will be a competition between cohesive failure and adhesive failure. So in my case also, I have to measure the interface delamination, interface toughness of the coating. So I want the crack only to delaminate from the substrate and not have a vertical crack. So in order to do that, I have gone through the literature, and there has been a lot of work which has been done on this, but there are one or the other difficulties or drawbacks which have been there in in all of these cases. As you can see that there is a probability of glue failure in this case. There is a probability of this 4-point bending geometry is a very popular geometry, but here we can see sometimes the asymmetrical crack growth which can happen. In case of modified 4-point bending also, there is a problem of glue failure which can happen. And this is also a modified form of 4-point bending. And this one is from our group only. But here, the only problem was that was not a analytical solution available to this geometry. And similar with this one. So in all of these cases, you will notice that there is the GC values, the interface toughness values are different. Because because the interface toughness value is dependent on the phase angle values, which is the phase angle, which is nothing but the ratio of shear to tensile mode. So here I have done the simulations of these geometry of my geometry first. So this is the cantilever geometry, which is fixed at this end, and the load is applied from this end. And this is the span length, and this one is the coating thickness H1, and H2 is the substrate thickness. So here A is the crack length, and this is the crack tip area, which has a very fine mesh for the calculations. And here you can see that the coating is at the topmost part, and the crack, the stresses are generated towards the substrate, which tells us that the probability of crack going inside the coating is very less, and as the substrate is ductile, so crack will not go inside the substrate, so it will move only along the interface. So in my experiments, I see a very clean crack. I will show it later. And here, these are some of the solutions of the J integral versus load values. And this is the analytical formula. And this one is, you can see that there is a very less error in the simulation and the analytical formulas. So here you can see that this is the fixture, experimental fixture, which I have used for my work. And this is the indenter, and this is the typical specimen. And here you can see the small crack length, the crack which has been generated with this experiment. So here you will see that there are various spots. These are for the purpose of doing DIC, we have done first the white spray and then a black spray for getting this speckle pattern. So the typical microstructure SEM image of the sample is like this. This is the YSD coating, and this one is the substrate. And for the experiment, this is the topmost part is the coating, and the bottom one is the substrate. So in the first, to generate a pre-crack, I have to load this specimen, and this pre-crack will be generated on its own after reaching a certain critical load, and then the load is removed, and then the sample can be tested for the first test. So here we can see that the A naught crack length will move towards the A1, and the critical load, this one P1 will be noted down, and this will be used to generate to get the analytical results and simulated results. Similarly, this specimen can be unloaded again, and then it can be loaded again. And similarly, the experiment can go on and on for as long as the substrate is not showing any plastic deformation. So this is the sample. You can see that the coating here, and this one is the substrate, and the crack has moved along only the interface. And as I have spoken earlier, that there is always a probability of there is a competition between the cohesive and the adhesive failure. So here you can see that when the coating thickness is very low, H1 by H2 ratio is very low, you can see that there is a very high chance of the vertical crack to happen. But when this crack thickness, when the coating thickness is higher, you can see that the driving force for interfacial crack is higher. So we want to keep our coating thickness higher as compared to the substrate thickness. And that is how we came up with the dimensions of the coating. And so here, can you please play the video? Both of them. So this is how I have both of them. This one is. So this is how I have measured the crack length with the DIC setup. Here are the vertical point probes, as you can see here. So crack has already reached the A1 line, and when it will reach A2 line, there will be a sudden movement in this this displacement in this A2 line probe. So from there, I get to know that there is the crack has reached this A2 point, but has not reached the A3 point. So here you can see that there is a sudden jump in the displacement of the this. So this is the typical load versus crosshead displacement of the experiment. And here these are point 1 and point 2. These are corresponding points on the these A1 and A2 lines. So here you can see that A3 line, this probe is not moving. So I get to know that the crack has not reached A3 line, but it has reached A2. So from there, I can measure the crack length in situ during the experiment. And from there, I can keep on doing the experiment. So here are some of the images from the sample before the test. This is after pre-cracking. This is after first crack, first test, second test, on and on. So I can do a lot of tests with just one sample. So, and this is the load versus crosshead displacement curves of some of the samples of one sample, and on which 8 tests have been done. So here you can see there is a slight deflection in the load versus displacement curve, which indicates that whenever crack starts to grow, the stiffness of the sample will drop, and this will keep on happening in every experiment. And so these are the typical values that I have obtained for the alumina over the steel substrate samples. So on the first sample, I have done 7 tests, and like that, these are the scatters, the typical values that I have obtained. And this one is for the YSG samples. And for doing this, using this similar geometry, same geometry, I have done some tests to assess the effects of substrate thickness and substrate roughness on the interface toughness values. So here you can see that with the change in substrate thickness from 4.7 mm to 2.7, there is a very less change observed in the interfacial toughness values. And similar was with it was the case with when the alumina was deposited on the same substrate. So here also the values of when the substrate thickness changes, there was very less change in the GC values. But the same is not true for the substrate roughness. When the substrate roughness increases, you can see that there is a very sudden change in the interface toughness values that are obtained. So for doing this, for understanding the reasons behind it, the simulation has been done. This is for the no roughness simulation, and this one is for the 5-micron surface roughness. And these are done in the Abbas with a 2D model. So here you can see there is a slight waviness has been given to the sample. And here you can see that the shear mode, the shear stresses are higher in case of this when the substrate roughness has been given to the sample. And this one, when there is no substrate roughness, the stresses of the shear stresses are very less compared to this one. And this one is the opening mode. Here also you can see the higher mode, higher stresses. And there is also this closure stresses are also present in the rough samples. So, and these are some of the typical values that I have obtained for the coating variation of the interfacial toughness with a change in coating thickness. So I have observed that with the increase in coating thickness, there is an increase in increase in interfacial toughness values. And we are still in the stage of characterization of these things, and we don't have enough explanations for these. So this is an ongoing research effort, and these are the conclusions. And thank you for your time.